The title of this video is Trigonometry But Good. That's because trigonometry is usually taught in a tremendously counterproductive way. My goal with this series is to reveal the true beauty of the subject obscured by those ridiculous methods. I will be assuming that you know and understand literally nothing about trigonometry, only very basic algebra and very basic geometry, so keep that in mind. And if you already know trigonometry, I encourage you to forget everything you've learned about it up to this point. As you may already know just from looking at the name, trigonometry is probably about measuring triangles for now. Since triangles are made out of three angles, before jumping into the trigonometry itself, we will start by talking about angles. Everyone knows what an angle is. It's the gap you get when two lines cross. And if all the gaps are the same size, they are right angles. There are many ways to measure how big an angle is, but for now, we actually don't need to worry about that. We can get pretty far without doing it. Right now, we're more interested, or at least I'm more interested, in figuring out what angles do, not what they are. However, we will still name angle measurements using Greek letters because it looks cool. Notice that since lines crossing are symmetrical, these two angles across from each other are identical, and the same is true for this other pair. We will call these pairs vertical angles. Often we'll have a situation where two different angles together will make one right angle. We will call these complementary angles. This term's important, so remember it. Note that this term refers to measurement, so two disconnected angles can still be complementary. For convenience, I will say that if one angle has a measure of, say, theta, the measure of its complementary angle is theta c. I don't know if this is a standard notation, but to be honest, I don't really care. Finally, you should notice that a straight line makes two right angles. Now we're prepared to deduce a very important fact about triangles. If we take two parallel lines and cut them diagonally, well, these two lines we just said are parallel, so they must be coming at the diagonal at the same angle. Otherwise, they would meet. That means all the angles up here must be the same as all the angles down here. And since these pairs of angles are vertical, they must have the same measurement, which I will again call theta. We can add a second diagonal to produce a triangle, and conclude as before that all these angles have the same measure, which we will now call phi. Notice that there's a pair of vertical angles here, and one of them is the peak of the triangle. We'll call their measure gamma. Now hold on a minute. We see now that all the angles inside the triangle are the same as the angles that make up this straight line. And we already know that a straight line makes two right angles as well. Thus, we have deduced that the sum of all the angles inside a triangle is the same as two right angles. Now, in order to check that you understand anything that's going on, I will present exercises throughout the video. You should really attempt these before continuing, since learning requires doing. Now, when solving problems, you should remember a few things. 1. If you can't figure out a problem, don't be afraid to try something that seems reasonable to you, even if no one has explicitly told you whether or not it is right. If it turns out to be silly, then you'll still learn that. Here, there's no pressure to be right anyway, so always try something. 2. When solving a problem, it is often helpful to label things, even if it's not exactly clear how it's going to help yet. Trust me. 3. Do not give up on a problem or assume that you're too dumb or need the steps just because it's taking you a while. Instead, realize that the problems you don't know how to solve are the ones that teach you the most. Now then, here are the 3 exercises. If you're already familiar with using algebra or calculations for these, I challenge you to do the exercises without them. I already discussed everything you need to figure these out like that. 1. Consider a right angle on top of a straight line, like this, and consider this pair of little angles. Also consider the pair of little angles in a right triangle. If we label one of the little blue angles phi and one of the little green angles theta, what's the other blue angle going to be? What's the other green angle going to be? 2. One important fact about right triangles, which we will use a lot, is the Pythagorean theorem. This theorem states that a square on the side of a right triangle slanted side, called the hypotenuse, has the same area as both squares on the side of the legs combined. A very nice argument that shows this is as follows. If you take the right triangle and make 3 other copies, You can arrange them to form a slanted square inside of a big square. Note the position of the short and the long legs. Now, the slanted square sides are all hypotenuse. Moving these triangles around in a big square, we can produce squares whose side lengths are the same as both legs of the triangles. But the area of the triangles didn't change, so these two little squares must take up the same area inside the big square as the slanted square. There is, however, one problem with this proof. There are some four-sided shapes where all the sides are the same, but that are not squares, such as what you get when you combine two triangles with all sides equal. Squares are distinguished by the fact that they only have right angles. Why can we be so sure that these angles in red will always be right angles, no matter how weird the right triangles are? So, for the first one, the simplest way to do it is to remember that two right angles make a straight line. Similarly, the internal angles of a triangle also make two right angles. Since in both figures we already have one of the right angles, the other two must make the other one. Thus, the pairs are complementary. We can actually see both facts at the same time by looking at this diagram from earlier and setting gamma to be a right angle. Figuring out that one of the pairs is complementary immediately gives us the other pair. For the second one, we can pick any little angle in any of the triangles to be, say, theta, and since all the triangles are the same, the other ones are theta as well. The other little angles within the triangles must be complementary to theta, as we've seen already. And now we see that in each corner of the slanted shape, there's a straight line and two complementary angles. Since straight lines make two right angles and these complementary angles make one of them, all the angles in the corner of the slanted shape must be the other right angle, confirming that this is a square after all. Alright, now that we have these preliminaries out of the way, it's time to get into the actual trigonometry. The basic observation that motivates right triangle trigonometry is that if you fix one leg of an angle in place and adjust the other leg, not only does it trace out a circle, which will be important later, it also forms a right triangle if we drop a line segment like this. From this, we see a clear relationship between the angles in a right triangle and its sides. And this relationship has a nice characteristic, which we shouldn't take for granted. If you look only at the length of the side that isn't part of the angle of interest, you'll never have two different angles produce the same length, and you'll never have two different lengths be produced by the same angle. This unique relation between an angle and the side is what motivates us to give an angle's corresponding side length its own special name. Due to a series of wacky translation errors, the standard name given to this side length, if the hypotenuse of the triangle has a length 1, given an angle theta, is sine theta, from the Latin word sinus, meaning breadth. Keep in mind that sine theta is just another number. We only gave it a fancy symbol because we don't currently know what it is yet. Now, the important thing is that we always label the side that does not form part of the angle theta as sine theta, regardless of whether or not the triangle is rotated around or whatever. We usually, for simplicity, call this side the opposite side. You should hopefully build a feel for how this notation is used to capture the orientation as you go along. As an exercise, pause now and figure out how to use the sine notation to label the other side of the triangle. Since that other side is opposite to the angle complementary to theta, you should have concluded that the other side of the right triangle should be the sine of the complementary angle to theta. Now, for triangles where the hypotenuse is not of unit length, the concept of scaling can help us. When we scale a shape uniformly, you can imagine that we are simply stretching or squishing the space that it is in by the same amount, both vertically and horizontally. Notice that this process doesn't alter the shape, it just makes it bigger. So, in a triangle that's being scaled uniformly, angles are preserved, they stay the same. Observe that scaling a right triangle uniformly by a scale factor, let's call it h, simply multiplies the lengths by that scale factor. The same is true for any other kind of triangle. Here, I drew it as if the scaling factor was greater than 1. But remember that we can make things smaller by scaling by a factor smaller than 1. Now, notice what we have here. In a right triangle with a hypotenuse of length h and an angle theta, we have side length h times sine theta and h times sine of the angle complementary to theta, respectively. Remember that this works because uniform scaling doesn't affect angles. So, if you only remember one single thing about right triangle trigonometry, it should be this diagram, since everything else should follow naturally. And you know what? Saying sine of the complementary angle every time, it's a mouthful. So it would be helpful if we just called the sine of the complementary angle the complementary sine, or even better, the cosine, and labeled things accordingly. Much better. Of course, you shouldn't see this change in notation as anything fancy. This is just a choice we made to make things easier to read. This is still just the sine of the complementary angle. You can keep writing it like this if you want. I don't want to though. Anyways, equipped with this new insight and notation, we will move on to the last set of exercises. 1. Label these right triangles using sine and cosine. 2. When two triangles are just uniformly scaled versions of each other, we say they are similar. Rotations and reflections do not affect similarity. Here, determine whether or not each pair of triangles is similar, and if they are, determine the scaling factor. 3. Consider a circle with a radius of unit length. We will draw a line that's touching, or tangent, to the circle, here, and connect the center of the circle to the tangent line in order to form a right triangle, where this little central angle is phi. Find a way to express the length of this tangent line segment using sine and or cosine. Hint: you may find scaling useful in this problem, but you can also just do things algebraically if you choose. Here are the triangles for the first exercise. Here they are using just sine if you prefer. Remember, the sine of an angle always corresponds to the side opposite to that angle. For the second one, after thinking about it, you should have hopefully noticed that since uniform scaling preserves angles, and all the angles will always make two right angles in a triangle, we can determine that all the angles in a triangle are the same as in others if we know just two of the angles are the same in both. Thus, pair A is similar, since we have two angles that are the same in both, with these scaling factors. Pair D is also similar with these scaling factors for the same reason. And B and C are not similar, since angles are clearly not preserved. For the last one, I will discuss both methods. If you gave up, which you weren't supposed to, then if at any point I say something that suddenly makes things click, pause the video and finish the solution yourself. Algebraically, you may start by labeling the side lengths, as I suggested. Let's call this hypotenuse h. We see that if this angle is phi, then this one is the angle complementary to phi, and this side length must be h times the complementary sine of phi. However, this length is already just 1, so these quantities must be equal. This implies that the length of the hypotenuse is just 1 over cosine phi. Finally, we can do what we've been doing this whole time. Since the hypotenuse is 1 over cosine phi, this side length, which is the length of the tangent segment, is just 1 over cosine phi times sine phi, or just sine phi over cosine phi. Alternatively, you could have looked at the original figure and dropped a line here, forming a right triangle whose hypotenuse is the radius of the circle, so its length must just be 1. We then label the sides as usual. Now, notice that both of these triangles have the same angles, so we should be able to scale the little one up to get the big one. We can tell from the position of the angles that the side with length cosine phi corresponds to the side with length 1. They're both the bottom sides from the perspective I drew things in. Thus, since anything divided by itself is 1, we can scale the little rectangle up by a factor of 1 over cosine phi and get the same measurements for the big triangle. This combination of sine phi over cosine phi comes up quite often, so it's valuable to give it its own name. Since it shows up when measuring line segments tangent to circles, the standard convention is to call this expression the tangent of the angle, and we notate it accordingly as tan phi in this case. Now, all of these notations are very nice and all, but how does this help us actually calculate exact measurements for the side lengths of triangles? Our plan of attack is as follows. First, we will devise a way to measure angles. Next, we will find sine and cosine for some basic angles using special right triangles. And finally, we will find ways to combine known values of sine to get new ones using creatures called trig identities. But that's a topic for the next video. See you then!